This is section 4.3 of the M3 Mechanics course, and it's looking at centripetal forces and applying circular motion to simple 3D situations. So I'm going to start off with a basic example and then go through some slightly more complicated examples. We start off with a particle of mass 1.5 kilograms attached to a light inextensible string, and it's moving in a circle. So the tension has two components, one causing a centripetal force and one upwards that's equal to the weight, and the weight downwards is equal to 1.5 g. Now, because the radius of the circle is 0.36 and the length of the string is 0.6 meters, we can find theta very easily, and theta is sin to the minus 1 of 0.36 over 0.6, which gives us sin theta is just 3 over 5, or cos theta is 4 over 5. It's a Pythagorean triple. So 1.5 g is equal to t cos theta. Okay, the weight is equal to the upward component of tension, and cos theta is 4 over 5. So we can calculate very easily that the tension is 7.5 g divided by 4, which gives us 18.375 newtons. Now, when we look at the centripetal force, we can set the centripetal force equal to the inward component of tension, which is t sine theta, and when we do that, we have 1.5 times by omega squared times by 0.36 is equal to 7.5 g divided by 4 times by 3 over 5. Now, there's a couple of things that cancel here. The 1.5 and the 7.5 cancel to make 5, and then the 5 and the 5 cancel, and so we're left with a nice simple equation of omega squared is equal to 0.36 times by 0.36 is 3g over 4, and so omega is the root of 3g over 4 times 0.36, so we get omega is 4.52. And that was what the question asked us to find. Here now we have a conical pendulum, the light string, and a particle rotating. Now, this is a nice little proof, so that's why I've done this question. It's quite an important one. So we find that theta is equal to L sine theta is equal to the radius. Okay, and we're going to use that fact. Now, the centripetal force is m omega squared r. So when we put those in together, we find that L sine theta, which is the radius multiplied by m omega, gives us the centripetal force. So if we just call that t sine theta, okay, the centripetal force, then we can equate the two, because it's the sine component of the tension that's equal to the centripetal force. And so what we end up with is the tension is this. Now, in cancelling the signs, we're ending up with an equation that's independent of angle. We've got L m omega squared is equal to the tension. Okay, so the tension is just varying with the angular speed. Quite important. Okay, it's a good little derivation to be able to do by yourself. And here I've just gone back to the original question to show you what it was that we were trying to prove. Now, in a similar vein, we can go on and we can look at a slightly different situation. It's still a conical pendulum, but here we can try and show what omega squared x is equal to g. So, a little bit more difficult. Just zoom in a little bit. We have that the tension is a component. A component of the tension will be equal to the weight, and an inward component will be equal to the centripetal force. So the same as before, we can set m omega squared r is equal to t sine theta. We can define cos theta as L over x, the length of the string, divided by the height at which the rotation is below that vertical point A, and R then is obviously just L sine theta. So, putting everything together, we have that m omega squared R divided by mg is equal to t sine theta over t cos theta. Now these will cancel, the t's will cancel to leave us just with tan theta, and we're going to be getting rid of the masses and getting just a term that's quite simple. Now x is equal to r over tan theta, so you can start to see maybe why this tan is very useful. So omega squared r over g is equal to tan theta. So omega squared r over tan theta is equal to g, and r over tan theta we showed was x. So we very simply get omega squared x is equal to g. Okay, just to go back to the original question, if you're a bit unsure of that one, I suggest that you look through it again. It's a very typical sort of proof. It's a very useful sort of proof that would be quite handy for you to be able to do in an exam situation. So that's it for me for examples on this topic, and the next video will be on the next section of the course. I hope this has helped.